So I did 2 presentations at Dockercon, and you can find those on the Dockercon website if you're more interested. There's one that's very flashy, talking about the spacecraft, and one that's a little bit more in depth about our entire CI dev process. So I'll give you guys a little bit of an overview on Dart, but really wanted to dive into the Docker stuff. So we're out of the Planetary Defense Coordination Office. It's responsible for finding and tracking near-Earth asteroids, or near-Earth objects, so anything that potentially could strike Earth. We want to make sure that we characterize those objects, and the Planetary Defense Coordination Office is actually responsible. The U.S. has given its charge to deflect or disrupt those objects that could potentially impact Earth. So DART is the first tech demonstration to hit one of those asteroids, and it is led by Johns Hopkins Applied Physics Lab, where I work. And so together, us and NASA, we're trying to knock an asteroid off course. So it's a 3-step process. Step 1 is to build the spacecraft. So you can see a rendering here. We have our imager, our high gain antenna. We have rollout solar arrays, which are pretty sweet, and we have an ion thruster. So that ion thruster is electric propulsion to get us from any orbit to the asteroid, and it takes a long time, but it's extremely efficient. Step 2 is for us to actually hit the target. So basically, we walk through our launch and our calibration. We have to do we have to acquire the target, identify the target. So we're doing some image processing on board. We have to select that target. We pop out a selfie set. We hone in on our secondary asteroid, and then we check out basically what we were able to do. So we have an impact, and the selfie sat flies by and says, okay, we saw a plume, or the ground station actually says that we moved the asteroid. So step 3, save the world. These are the same slides from Dockercon. So basically, we're validating that this thing works. We're trying to make sure that if an asteroid was coming towards Earth, that we would be able to do something about it. So why did we choose Docker? So space has a whole bunch of problems. Space has a whole bunch of things that will kill your spacecraft and cause engineering issues like vacuum and radiation, and you have super low power. Your thermal is all over the place. But all of those factors drive cost and reliability. Your processing is super low memory. You have a really small CPU, really low processing power. And the big thing that you have to get right is you have to get everything right the first time. So we test everything an enormous amount. So the big thing that Docker really bought us is this automated testing and this parallelized testing suite. So we don't have anybody that can go up and fix your spacecraft yet. The space shuttle isn't there anymore. So you got to get it right the first time. So originally, it was a whole bunch of hardware that we would have to buy, and each developer. Well, so in practice, you would want each developer to have a test bed, but that's not practical because they were so expensive. And what we were able to do with Docker was essentially software emulate all of these things, all of that hardware, and now everybody has basically just works on their own laptop. And we have a parallel CI/CD system that's able to run multiple simulations at one time. So the way that we did that, we heavily relied on the Core Flight Executive. So this is basically a hardware abstraction layer from NASA, which is open source. You can go get it right now. If you look up Goddard CFE, and what that allows is I can build the same C program and the same C applications that I am writing for VxWorks, for Artems, for Linux. I can run it on a Raspberry Pi. I can run it on an NVIDIA Jetson. I can run it on a Leon 3. Or a RAD 750. Basically, it gives you both operating system abstraction and hardware abstraction, and it lets you run anywhere. And that was a key piece because that is our emulation layer for this code. We used Bamboo for our CI/CD suite, and we moved to a network architecture. So previously, most spacecraft have a processor in the middle. It looks very much like an embedded system. So you have a processor in the middle, and you have UARTs, or you have SPI, or you have direct links, GPIO, for example, that are all linked out to the specific components. And that's really, really hard to model without having the real hardware, because then you have to emulate every single one of those different links. Because we moved to SpaceWire, those links now look a lot like UDP. And so when I show you guys the compose files, you'll see where we're just opening up ports, and those are what look like a SpaceWire network to the rest of the spacecraft. We are also using Cosmos. Cosmos is an open source ground system. So both CFE open source and Cosmos open source. That ground system is out of Ball Aerospace, and that gives us an ability to basically use a lightweight Ruby-based ground system that's maybe not completely full-featured, but pretty easy to set up, relatively easy to set up, and we Dockerized that so that it became super easy to set up. And now we can have instances of ground systems where normal ground systems are multiple gigabytes and very big processing hogs. This one is very small, and so it lets us run 5 of them at a time. And then, of course, we took all of this and Dockerized it, which is why we went to Dockercon in the first place. So I think this is what you guys really wanted to get into. How did we do it? So we have 4 repositories. We have the flight software, which is all of the C code that is on the spacecraft. We have our testbed software, which is all of the emulations of the rest of the spacecraft. So your star tracker and your power units and your temperature sensors, things like that. Cosmos, which is the ground system. And then we have an environment repository. And that environment repository essentially is the glue that holds all of those 3 things together. So each one of those, so the flight software, the testbed software, and Cosmos, each one of those are kind of distinct units, and in theory could be used on their own. So we didn't build in the Docker, like Dart flight software doesn't have Docker files associated with it or Docker Compose in the repo. We actually have it so that if you wanted to build it in the legacy way on a computer that is set up with the right tool chains, you could just download that repo and build it. That kind of decouples Docker from the actual, I guess you would call them applications yourself. but we use this on our team exclusively with Docker because it gives us so much more. So what we do is we build 4 containers. So that FSW Docker repo has all of our Docker files and our Docker Compose files. And we have 4 containers. So flight software, testbed software, Cosmos, and then we have a VNC container, which actually gives us our link between Cosmos, the Cosmos Docker container, and a display page out. So we're able to have a we don't have to do any weird X forwarding stuff or open up too many security vulnerabilities because we have another container that's actually handling that. We have runtime voluming of the source code. So this has actually been up for discussion a little bit, but we've decided to stick with it. Basically, these repos, the Dart Flight software, Dart Testbed software, and Dart Cosmos, what we can do in there is we don't build an application and then add that in our Docker file every time we build. We have a Docker container that has the environment set up, and we volume the flight software, or we volume the testbed software code and binaries in at runtime, which gives us an ability to just build and rebuild the code without having to rebuild the Docker container, which actually saves us a decent amount of time, allows us to play around with it inside the container, allows us to do live debug, which is really, really nice. And kind of it was a design strategy that's not portable to true deployment in the Docker sense, but since we're deploying to embedded targets anyways, there is an additional deployment step. So we can't actually deploy our Docker containers. We are deploying embedded binaries that we are building inside of our Docker containers. And then the original reason why we went with Docker is because we wanted to keep our cross-compile toolchain standardized. The same way that you got to keep Python and Ruby all figured out with what versions you're running and what gems you have, and that's one of the reasons why Docker is super, super nice, because it keeps that environment set. We have the same requirements on our end, but with C toolchains. So we have a specific way that we use our cross-compile toolchains. We have a specific set of libraries that we need in the right place. And so Docker keeps all of that in one area. As far as, so now that we have those 4 Docker containers, you can see each one is kind of in blue. We actually have the flight software set up to talk to the testbed software. So you have your UDP messages going back and forth, which actually look like SpaceWire. And we're able to build in a library that instead of having to rewrite large pieces of code on the flight software, we have one library swap that we're able to say, go from SpaceWire to Ethernet, and everything else looks the same to the system. So it's all about emulating the pieces that you can pull out in a modular fashion. So you have essentially network between the flight software and testbed software, and then you have between the testbed software and Cosmos. And so the testbed software to Cosmos acts like your radio. So you can see that here. And then Cosmos also supplies the testbed with, hey, I want something weird to happen. It can send up anomalies, essentially. And then the flight software to testbed software is just looking like that SpaceWire link to the rest of the spacecraft. And then going out, we have Cosmos talking to that X11, the VNC Cosmos container, or the VNC screen container. And so that allows us to actually view what's going on in Cosmos. So for the VNC window, basically what we needed to do was we had a heavyweight application. So Cosmos was a heavyweight Ruby application, or is a heavyweight Ruby application. And you can run it headless, which is really, really nice for automated testing. But if you want to peek and poke around with what's going on in the flight software, you have to be able to look at this this GUI essentially. And so we tried a couple of different things. We were originally X-forwarding out of the Cosmos. Well, originally we were using Cosmos natively, but that doesn't necessarily scale because then you don't have a nice Docker compose file that has everything in it. But the so basically we were trying to find a way that we could get a GUI out, and the answer that we came up with was to use somebody else's answer that they came up with. So Jan originally did this, and he built an X11 client and an X11 server that were super, super small Docker containers that essentially the client just exposes your X11 application. So as long as you can X forward from that application, you're good to go to the X11 server. That X11 server is actually what handles all of your X11 port forwarding and then opens up a VNC client. So the security vulnerabilities that you have from opening up an X11 server that Cosmos in the Docker container can forward to are all contained in that Docker container. So you have Cosmos sharing this security key with the X11 server. You don't have to do anything on your personal machine. You don't have to open anything. All you have to do is VNC in with your favorite VNC viewer, and even just normal like Firefox or Chrome will sometimes work. And then lastly, we have Eclipse that's giving us. So Eclipse does a lot of the Docker tooling as well. What ended up happening was that Docker tooling ended up being slightly different. So the Eclipse setup runs the Docker files and the Docker Compose files in a very similar way, but because it doesn't have, it didn't have Compose functionality when we first were starting up, we had to actually start those Docker containers by hand. But effectively, because you're using those immutable Docker images, they look the same way in the end. And what we're able to do is run everything from Eclipse. We're able to debug, like live debug through to the flight software. So Eclipse to the Docker container, and then Docker container to flight software, which is running a GDB server inside that Docker container to actually pass messaging back and forth. We're able to do the same thing with our flight hardware, and we're able to basically run all of those things together. I was not the person that put together the Eclipse stuff. Justin was, and if there are a lot of questions on that, then we'll figure out a way that we can stay in touch and hopefully get you guys answers. So what I wanted to show is a little bit more on what this actually looks like. So we showed this at Dockercon, but didn't actually dive into it. So this is the same setup that I showed earlier. So we have Docker Compose files, we have Docker files, we have our pre-built, which is all of our binaries. We have our shared environment, which is our submodules. So Dart Cosmos, Dart Flight software, Dart testbed software. If there are other repositories, so if you were setting this up in a different way, whatever repos you need, we essentially had a structure where shared environment is where we put our other pieces. So if you wanted to have a multi agent situation, for instance, then you could have the agent themselves be repositories or applications that did something, and you could have your car agent, and you could have your airplane agent, and you could have your insert whatever you need there as a part of a multiple piece system that other like our teams are actually separate. So we have a different ground team from flight software, from testbed software. And so everyone's updating those independently and can work on those in whatever environment they want. But our testing suite is all together in one. So we can make updates, testbed software can make updates, and all of those get pulled in. So additionally, we have our utility scripts, and that's just a whole bunch of things to handle some of the more specific space-related, like loading of a binary to an embedded system. And then we have a list of our Docker, basically helper functions. So our Docker build builds all of the all of our Docker containers. So it's essentially a shim for Docker Compose up, but make sure that all of our environment variables are in line because we're using Bamboo, and you can see that we're doing a couple of things that are not necessarily as easy as just Docker Compose up. We have to set a couple of things ahead of time. So that's what Docker build is. You have run dev, which we showed. So our run dev basically is, I guess our Docker build is our Docker Compose up dash build. This is our Docker Compose up for real with our YAML file. So you can see our Docker Compose file here. And essentially we have 4 services. So we have flight software, we have our VNC display, we have Cosmos, and we have testbed software. And so if you think about these as 4 different agents that are all working together, we're doing everything in an instanced Docker Compose file. And what this allows is we can run this. This is our run dev Docker Compose file. It looks extremely similar to our run test. So you could see the output here where Cosmos, flight software, and testbed software is all talking to each other. I will run the run test now as soon as it's done. I didn't.
Can you zoom in a little?
Yes, I think so.
Okay, thanks. Yeah, that's it. Yep.
Okay.
Thank you.
So if we want to run, so this is running a test for autonomy, for instance. So this is in run dev, it's basically just a exploratory, I guess is the best way to put it. So it gives you the Cosmos, it gives you the GUI that you can peek and poke around and see what's happening. The run test actually runs a Cosmos unit test, and so it gives you this essentially a framework that you can send commands up to the testbed through the testbed to flight software and get telemetry back and check it. And so by using this, we're able to actually have automated tests for Cosmos, and we're able to have automated tests for Cosmos that we can use in Bamboo. And so other than that, I think that that's a pretty I think that that's the overview of the Docker components and how we used it. I'm more than willing to take questions. I've never done questions over YouTube, so we'll see how this goes. Yeah, happy to answer any questions that I can.
Christopher, I wanted to ask, other than Bamboo and Docker, do you use any other DevOps tools for your CI/CD or deployments, or do you use any clouds?
So because of the nature of space, we don't do any cloud-based work. Essentially, everything has to be on premises. We have essentially bought into the entire Atlassian suite, which is not necessarily a bunch of DevOps tools, but we use Jira and Bitbucket and Bamboo and Confluence, and those are kind of the main pieces. We have talked about using Artifactory for handling some of our deployments to our test beds, but we aren't actually planning on doing. I don't think that that's going to happen anytime soon. Basically, we just brought in DevOps for this mission, so we haven't done anything like this before, and we started this mission about a year ago. So we are brand new to Docker and brand new to DevOps, and so yeah, we're also open to recommendations.
I wanted to ask, like you build Docker images. Are they like fairly large, or they small in size? I mean, how do you
They are actually they're pretty big. So let me. So our Docker images, we even tried to make them smaller, but a set of Docker images, because we're tagging for each different build, so our test bed is not too bad, but the rest of them are somewhere in the 2 gigabyte range, and our X11 server is small because that was originally small. But so a couple of things blow us up. One, Cosmos itself has a ton of dependencies, and so it's got a slew of Ruby gems and dependencies that you have to pull in that cause a significant amount of bloat. And the Dart Flight software, because we essentially just continued to add more and more tools to it, because that is our environment that we work and play in. So we don't have a separate build and a separate run for flight software, which is something that we have talked about going to, because that would significantly slim us down. We had something where we got it down to 300 megabytes for a run, which would be really, really nice, but it didn't actually buy us anything time-wise, which was really, really surprising. So the biggest problem is our builds take a while.
Hey, hi, Christopher.
Yep.
I just have a small question that the information in the space will be sensitive. So how you are trusting containers, like they are reliable to some extent, and you're not using any orchestration tools as of now. So if something fails in the container, then how will you handle it?
So we aren't actually. This is only for testing. It is only for development. It's not for anything in production. So our code, like the C code that we write for flight, is the end testing is all on real hardware and not using Docker. So basically, if we have a failure in Docker, as long as we can tell that it was a Docker failure, we're fine. If it's something else, I mean, we have found real problems in our flight software doing this, and usually they show themselves pretty easily. We've had a couple of issues with Docker where I think I have a lessons learned page. So we had a couple of issues with Docker where we tried to originally we had static IPs, and those caused serious problems because we were trying to bring up multiple of the same compose file, and the IPs were actually stepping on each other, like the subnets were stepping on each other. So that didn't work. We had problems with our essentially when you overload the Docker daemon with trying to bring up too many basically trying to run too many of these in parallel, you can have it crash. And we also have an issue where MQs are not actually being abstracted properly. So basically, we will run out of MQ space after running 4 of these setups, 4 of these instances, because Docker doesn't actually abstract it away, and it reaches the kernel limit, and then things soft fail. But as far as what happens when that fails, we just chalk it up to Docker had a problem, and we're able to rerun it in Bamboo.
Okay, I get it.
Hopefully that answers your question.
Yeah, and one more thing, I just want to know that you are showing your deployment files, like not I'm not clearly, I didn't get it clearly, but you told that your build images is like a huge one, right?
Sorry, can you repeat that last part?
You said that your build images are are huge in size.
Yes.
So you can reduce. So are you using any multi-stage builds to? Have you tried to use multi-stage builds to reduce the size of the image, or are you just going by the traditional way, like it's in a native state as of now?
So we are not doing multi-stage builds. That was one of the things that we picked up at Dockercon that I think that we could explore or should explore, but we haven't gotten into that yet.
Okay. Because I thought that if you are using multi-stage builds, the image size will be quite less than what you are having right now.
Yeah, I that's a good point. Yeah, I'm definitely. We tried to pull back. We looked at multi-stage builds, and we looked at trying to split the build and the run environments as well. And so the biggest issue that we're having right now is I think that whenever we're pulling in context, that takes too long. The builds themselves are very quick once you pull in all of the context. But yeah, we should check out multi-stage.
Yep. And can I know that how this space thing got into containers, how this entire idea came up with, like why containers for this?
So it honestly came down to I wanted to standardize our toolchain, and it wasn't supposed to get this big. So I wanted to standardize our toolchain and how we built things, because when I was first handed this, it was, okay, you need to put this here, and you need to make sure that you wave your hand like this. And it was a very convoluted, brittle system. And so when we took it, we said, okay, well, if we Dockerize this, then everybody will build it the same way. So that's how it started. And then we started looking at, okay, well, now that we have this building and running in a Docker container, can we add a ground system, and can we add our test bed? And so that it just kind of evolved.
Yeah. Thanks a lot. Thanks a lot, Christopher. That answers my question, and hope this space journey will continue to extend.
No problem. Thanks.
Christopher, how do you guys maintain your security auditing in these Docker images? I mean, like, how do you handle security vulnerabilities?
So as far as security goes, we're only doing these. So we're not deploying these to anywhere outside. We are. They're only on either our laptops or our internal network. And we also try and make sure that we have vetted all of the containers that we're pulling down. So like we're not trying to pull down. There was a slew of security issues with tainted Docker images. We're trying to pull down only the ones that Docker itself is releasing, besides Jan stuff, which is a Docker file and not an actual Docker image. So we're trying to make sure that we, one, know what we're running internal, and two, we're not exposing that anywhere besides our personal computers. So that's, I don't know if that answers the question, but basically we're running underneath the IT shield, I guess, is the best way to put it.
Okay, and like, can you answer what components of Docker you guys are using other than are you just using Compose, or is there anything else?
Yeah, so it's Docker and Docker Compose. We haven't done. We talked about like how could we do this with Kubernetes or with Swarm or any of those, and at the end of the day, I don't think that those necessarily buy us anything. We're not looking for uptime. We're looking for instances. So Docker Compose gives you here's your environment, here's your instance of multiple containers and how that network is set up. And that's really all we need.
That's good. Does anyone in the Hangout chat, Hangout call, have any question?
Nope. That's it from my end. Like Christopher has answered my questions, and I'm good with it.
I guess we are also running out of time as of now. So Christopher, I would like to thank you for taking your time out and sharing your knowledge with us. And we will continue to get other questions answered from you as well. Other than that, I will be sharing the slides with you. And if anyone has any clarifications or queries after this session as well, you can get in touch with me, and I will get those from Christopher as well. Thank you to the attendees, and anyone has any. Thank you to the attendees and Christopher as well.
Awesome.
Thank you, guys. Yeah,
Thanks,
you,
everyone.
Thanks, Christopher. Thanks a lot, everyone.